Well, he says on section 22, 5 and 12. Yeah. Section 3 and 4, he gives two numbers.
Okay. So 5 and 12. So real quickly, we could do this one. This is kind of like the one we did a while ago. We have points on a parabola, 0, 0, and 6, 0. So is that going to be, and also they tell us the vertex is at 3, 9. So the vertex is up here. So is that parabola going to be one that's opening up or down or left or right? Yeah, it's going to be that way. So our vertex is at 3, 9, so that's HK. For a vertical parabola, that's x minus h squared equals 4p y minus k. So x minus 3 squared equals 4p y minus 9. So we just need to use one of these points to find p. Doesn't really matter which one we pick. I'm going to just do this one. So to find p, if we put a 6 in for x and a 0 in for y, we get 3 inside squared, so 9. We get 4 times negative 9, so negative 36 times p. Or if we divide both sides, we get p to be negative 1/4. Bless you. So if we know p, then we can substitute in there x minus 3 squared equals 4 times p times y minus 9. Of course, the 4's cancel, so we could call that x minus 3 squared equals negative y minus 9. And then there are all different ways you could write that. You could leave it like that, think they probably solved that for y. They actually, the answer I have, they even multiplied that out, the x minus 3 squared. That's not completely necessary. You could call that, so that'd be minus 9, or minus y plus 9. If we solve that for y, that'd be negative x minus 3 squared plus 9. So you could write it like that. So different ways we could write that. But again, it goes back to like the one with the beam that we worked. You write the generic form, you plug in your vertex, and then to find p, you use a point on your parabola. And as long as you know the vertex and one other point, you can find that equation. All right. So that was 5, 12. Copy this again. All right, a cable of a suspension bridge is suspended in the shape of a parabola between two towers that are 120 meters apart. So we've got a parabola doing this. The distance between these is 120 meters. The roadway is here. The cables touch the roadway here. And the top of these towers are 20 meters above. And they even give us, they say that this is the origin. Then if this is 120 meters between, then this is to the right 60, up 20. This is to the left 60, up 20. So if this is a vertical parabola, again, x minus h squared equals 4p y minus k. If our vertex is at the origin, then h is 0, k is 0. So then if we want to get p, we just substitute in. One thing where this one is better or easier than 11 is notice both units are in meters, so we don't have to do any unit conversion. So if we take one of our ordered pairs, 60, 20, we can put a 60 in for x and square it. 20 in for y. So 3600 equals 80p. Divide by 80. What you could do, you could divide just by 20 and find out what 4p is, because the 4p is what's going to go out front. So if you find out how much 4p is, then you'll just replace 4p with that amount. But we can find p. 45. So if we take that, x squared is 4 times p, which is 45, times y, or x squared equals, what's that, 180 y. Or you could solve it for y, divide both sides by 180. Notice what I was saying, if we did that, we would have 3600 equals 4p times 20. So if you divide both sides by 20, you get 180 is what 4p is. So if you replace 4p with 180, you can have that. All right, so that's 10.1 and 10.2. So we worked quite a few out of there. So let's look at 10.3 and 10.4. What out of 10.3, 10.4? 4? So they give us a parametric equation, a set of parametric equations, x defined by theta, y defined by theta, and they give us a graph. This is what that graph looks like. It's basically a spiral. If we let theta increase, and this would just continue to spiral. So we want to find, in the interval from 0 to 2 pi, the vertical tangencies and the horizontal tangencies. So to get tangencies, we need what? We need slope. So we need dy over dx, which means we need dy d theta over dx d theta So if we take the derivative of x with respect to theta, what's the derivative of cosine? Negative sine. And then how are we going to take the derivative of that part? Product rule. So it's the derivative of the first. What's the derivative of theta with respect to theta? 1 times the second factor plus the first times the derivative of the second. So if this is the first and the second, what's the derivative of the second? Cosine. So minus sine, plus sine, those cancel. So dx d theta is theta times cosine theta. dy d theta, if we take the derivative of this with respect to theta, the derivative of sine is cosine minus whatever we get when we take the derivative of that. So the derivative of theta is 1 times the derivative, or times cosine, plus theta times the derivative of cosine. So u prime v plus u v prime. Notice cosine theta minus cosine theta, those are going to cancel. And then this is going to be minus theta sine theta here. So that's going to be the opposite of that. So plus theta sine theta. So dy, so negative theta sine theta, theta cosine theta. So dy d theta, oh, actually, let's see, it was this, dy d theta over dx d theta. So if we want horizontal tangencies, we want to find when which value or which part of our fraction is 0. What's the slope of a horizontal line? 0. So if we're looking for our slope to be 0, which part of this needs to be 0 for this to be 0? The numerator. Yeah, that's supposed to be positive. That dy, so this is this one. Yeah, because it was a minus inside here. It was minus a negative, so positive. So in order for that to equal 0, notice this is a product. So either theta equals 0 or sine theta equals 0. So if we think about our unit circle, and we're going from 0 to 2 pi, where on the unit circle is sine 0? Which coordinate on the unit circle is sine? The y. So y is 0 here, y is 0 here. So at 0, at pi, and they say go all the way to 2 pi. So if we include 2 pi is one of those values. So 2 pi. So all of those are values that would make our slope 0. Now let's check something out. Notice they don't include 0. They include pi and 2 pi, but they don't include 0. What do we get on bottom if we put a 0 in for theta? 0. So is our slope really 0 at 0? No. Our slope is undefined at 0. So we can't include that one. So pi and 2 pi, that's where we have horizontal tangent lines. Let's see. We have vertical tangent lines anytime our slope is what? Undefined. The vertical line has an undefined slope. So if we look at our derivative, what part needs to be 0 for that to be undefined? The bottom. So if we take the denominator, set that equal to 0. They're not going to include the 0 again, partially because you could reduce that. So basically we want to find out what makes cosine 0 in the interval from 0 to 2 pi. Well, cosine is the x-coordinate, so cosine is 0 here and here. So at pi halves and 3 pi over 2. So those are the angles, those are the thetas for which cosine would be 0. If we put a 0 in, that's actually indeterminate. It's not undefined. It's not strictly undefined. Also, at 0, since our interval goes from 0 to 2, notice in our interval here, it doesn't include, 0 is not included in our interval. Right, so these are vertical, those are horizontal. And let's look at our graph. It's easy to confuse this with a polar graph, but this is not a polar equation. Notice we have vertical tangencies here and here, and those values of theta are pi over 2 and 3 pi over 2. But notice that's not in a direction pi over 2 or 3 pi over 2. That's not in a direction pi over 2 or 3 pi over 2. So remember, when we do polar graphs, a point is given by its radius and its angle. But when we have a parametric equation, we weren't confused ever if we had x equal something in terms of t, y in terms of something involving t. If we called it t, we didn't ever confuse it and say, well, whatever angle I put in, that's the direction it's going to be in. Our parameter just helps us define x and y. That really has nothing to do with the direction on the graph in a parametric equation. For example, when theta is pi over 2, when theta is pi over 2, x is, let's see, 0 plus pi over 2 times 1. Y is 1 minus 0, so 1. So when we put a pi over 2 in for our parameter, that doesn't mean that we're going to get a point that's in the direction of pi over 2 in a parametric equation. Our point is pi over 2 to the right, 1 up, which is right there. So we ended up actually right there. Not there. So right there was our point. Pi over 2 to the right, 1 up. And that's where that vertical tangent line was. So that's easily, you'll see how that can easily be confused. That when we put a value in for theta, if it's a parametric equation, saying that we're plotting our point at 90 degrees, we still have to calculate x and y. That's just a parameter. Think of it as a t, if that would be less confusing.
So it doesn't start at the origin? Or is that where that?
Let's see. So if we put a 0 in, it says technically we don't go to 0, but if we put a 0 in, cosine of 0 is 1, plus 0 times something, so 1. If we put a 0 in, we get 0 minus 0, so 1. So we actually start here. Not there. Yeah, over to the right. So that's where we start. Yeah. Which is somewhat a coincidence that actually is directly to the right, and that angle is 0. But that's not always going to work out. The direction of your point and the direction of theta are not always going to match. When we plotted a direction of pi over 2, that wasn't straight up. That was right there. If we plotted a direction of pi, I'm sorry, not a direction of pi, a parameter of pi, let's see. We put a pi in, we get -1. Put a pi in here. Minus pi, and so pi. So when theta equals pi, that corresponds to that point on that parametric curve. Pi, 2 pi, right. Well, let's see. We put 2 pi in, then that's going to be 1. So to the right 1. If we put a 2 pi in here, then we're at minus 2 pi. So to the right 1. So roughly right there is where we'd be at pi, or 2 pi. Theta is 2 pi. All right, what else? Let's see. Find the area of the region. So they give us, remember, if we want to find an area underneath a curve, then we integrate our function dx from a to b, where these are x values. Well, in terms of a parametric equation, if, let's see, how they do this. Let's copy this over. Excuse me. So we integrate our function with respect to x from one x to another. That gives us, as long as our function is positive, that gives us the area from A to B underneath our function. In terms of parametrics, we integrate t f prime of t dt, where we can call this g and this f. Make sure I don't have these backwards. Yeah, so those are. I'm just trying to. Yeah, I'm just trying to make sure that I don't have these backwards. So we're putting this value in. Okay. Yep. So f is the function y, x is the function g. So they confuse it with this notation. It's basically x of t, y prime of t dt. So that's the version of the parametric equation that you use to find the area underneath the curve. So this curve is a function f of x, but it's also given by the parametric equations x of t, y of t. So A, we can get that. I think I told you backwards, didn't I? This x value we can get from plugging that in t1 into the function f. Sometime we plug into the function f, we get these. So these are backwards, aren't they? So f y is your g. I knew that didn't look right. So it's f of t x prime of t dt. That makes more sense. It's just books write it using different notations. Generally, when we think of f, we think of y. But if we look, take this, for instance. And then let's look at, compare that to if I have some things I'm going to have, I can get dx dt, I can get dy dt, I can get x, I can get y. So in their equation here, if f prime, if f is x, then f prime is dx dt. So they basically have g, which gives us y, f prime, which is dx dt, times dt. Notice the dt's cancel. So that's essentially the integral of y dx. So if we call this function f, that function g, the dx over dt's would cancel. That would be dx. That's y. So it's your y parametric part times dx dt times dt. So we want to integrate integrate y, which is 3 sine squared theta tangent theta, times dx dt, or in our case dx d theta. So if we take the derivative of this with respect to theta, the derivative of that, 2 is a constant, bring the derivative of sine squared is 2 sine theta times the derivative of the inside. Say that again. If you've got 2 sine theta squared, if you want to take the derivative of that, you've got a 2 out front, bring the 2 down, sine theta to the 1 less power times the derivative of the inside. So 4 sine theta cosine theta. So this is y. Dx d theta is 4 sine theta cosine theta times d theta. We want to integrate that from theta equals 0 to theta equals pi over 2. So again, the notation that they used was confusing, but this is y at theta. This is dx d theta. And this is times d theta. This is with respect to theta. So let's see. Tangent, keep in mind tangent is sine over cosine. So what happened to those cosines? Cosines cancel. Let's see, 3 times 4 we can bring out front, that's 12. We have sine squared, sine, sine, so sine to the 4th. Or we could call each of those sine squared. And let's see, our rule was if we had a sine and cosine, we kept one and changed everything else into the other. But if we only have one, if it's even, then that's when we had to use that identity. And that was what? 1 minus cosine 2 theta over 2. 1 minus cosine 2 theta over 2. So, right. We can bring the 4 out front on bottom, 12 over 4. Multiply that out, that's 1 minus 2 cosine 2 theta plus cosine squared 2 theta. That first one, we can even integrate that second one. But that third one is a cosine squared, so we have to do that identity replacement again. And cosine squared 2 theta, that was 1 plus cosine of twice that angle. So if this is 2 theta, when we replace it, it becomes 4 theta. Remember, the identity was cosine squared of an angle is 1 plus cosine of twice that angle over 2. So if our angle when we had our squared was 2 theta, then when we change it to our cosine to the first, we double that angle. Now all of those are things we can integrate. I won't go through for time's sake and integrate all of that, but we can integrate a constant. We just have to do u du fit there, where we let that be u, so du would be 2 d theta. We could break this up into 1 over 2 plus 1/2 cosine 4 theta. So when we integrated that, that would be u, so then we would need 4 d theta. So you could just integrate those separately. Once you integrate all of that, multiply it by 3, and then evaluate it from 0 to pi over 2. They made that a lot harder than it had to be because of the way they gave us the function. I guess the way they did, the reason they did it in that order, because X and Y are in alphabetical order, F and G are in alphabetical order, so F corresponds to the X parametric, Y corresponds to the G parametric. But that's just confusing because normally when we see, or at least for me, when I see F of X, what are you taught in high school? F of X is the same thing as Y. Yep, that's right. That's right. They give it to you right here. They give you a theta, starts at 0, goes to pi over 2. So we looked at calculating area with polar graphs yesterday. So when we looked at just regular rectangular coordinates and rectangular calculations, when we did the Riemann sum, as long as F was positive, that gave us the area under a curve. For our parametric equations, y of t x prime of t dt from t1 to t2 gives you that area. For polar, what was it, 1/2 the radius function squared d theta gave us the area. So all of those are integrals, but we're adding up different things. Here we were adding up basically a rectangle. Here we were taking, let's see, the change in x this is still basically a rectangle. This gives you the change in the x times the corresponding y value at a certain t. But here we were adding up sectors. So find an area. These two are using the same shape. We're just taking that and converting it into parametric form. Here we actually had we didn't so much do a straight conversion from here to here as we found a formula that gave us the area of a sector, and that area was 1/2 r squared theta. So we broke that up into little pieces. Our d theta is what we were letting vary. So we're adding up all those r squared thetas from one angle to the next. All right, so what other homework problems? Any more out of that 10.3, 10.4 section? Let's do that 10.5. 10.5, probably the hardest thing in this chapter that we have to deal with because of the graphs. So let's look at some problems from 10.5. So they give us an equation, and then they give us the corresponding graph that goes with that. This was number 1, and yeah. I'll just get the corresponding graph. It looked like this. They said find that area. Or actually they said write an integral that would give you that area. So in polar form, if we want the area is 1/2 the integral from theta 1 to theta 2, bless you, r of theta squared b theta.
You said you could write it in that other form, or what was that other thing you wrote? You just wrote it without parentheses, right? Earlier?
I may.
Squared theta, b theta?
I guess so.
Yeah.
Yeah.
Same thing.
Yeah. Hey. I don't know. I don't know, probably 30 minutes or an hour, something like that.
I'll see you.
Okay. So our R function is 5 sine theta. That's going to be squared times d theta, and we just need to find out what angles give us this portion of the curve. So if we were so this direction would be theta 2. That direction would be theta 1. So notice when we first start out, if we put a 0 in for theta, what do we get? What's sine of 0? 0. So this point is in a direction of 0. And then as our angle increases, then we get bigger and bigger and bigger and bigger until we get to theta being pi over 2. What is, when theta is pi over 2, what's sine of pi over 2? 1, so we get 5. So remember, this is a polar graph. A while ago we said we had a parametric set of parametric equations. The angle wasn't necessarily the direction. Here, the angle is the direction because it's a polar graph. So this point was in a direction of 0. This point is in a direction of pi over 2. So if we want the area inside that region, we want to add up all of the area starting from here. And then if you think about adding up lots of little sectors from here to here, here to here, here to here, here to here, we're going to add up sectors until we get to that angle. So we're going from 0 to pi over 2.
That's the hardest part.
Yeah, that's often the hardest part. If we squared that, we would get 25 squared, or 25, which we could pull out front as 25 over 2. Sine squared. And again, we won't go through all the way through that integral because we did that integral 2 or 3 times yesterday. What do we have to do to integrate that? We have to use that double angle identity. Or sometimes you'll hear it referred to as a power reducing identity because it reduces from sine squared to something to the first power. And that was 1 minus cosine 2 theta over 2. So that's all they were asking for. I don't even know if they didn't even ask to integrate it there. The next one, r equals cosine 2 theta. We'll generate that graph, and then let's find out how we would calculate the area of that left pedal. So you'll have this. So if we have r equals 2 theta, if this number is even, we have twice that number of pedals. So for ours, we have 4 pedals. If they're evenly spaced, they're 90 degrees apart. The tip of the first pedal, we said for the cosine ones, the tip will always be on the x-axis at 0 degrees, because if you put a 0 in, you get cosine of 0, and doesn't that give you the largest possible value for cosine, which is 1? So in a direction of 0 degrees, we're out 1 unit. If our tips occur 90 degrees apart, then we go 90 degrees and get another tip, 90 degrees, get another tip, 90 degrees, we get another tip. Let's also find what angles give us a radius of 0, because that'll give us our tangency at the poles. Remember, if our radius equals 0, then theta equals whatever that angle is a tangent line at the pole. So let's sketch those. That'll help us with our 2. So keep in mind theta is between 0 and 2 pi. So when we're looking for angles for 2 theta, if we double this, 2 theta can actually be between 0 and 4 pi. So when we're listing at what angles we would get a radius of 0, we need to list all angles up to 4 pi. And I'll show you why in just a second. So if theta can be anything between 0 and 2 pi, 2 theta can be from 0 to 4 pi. So cosine is 0 at pi over 2 and at 3 pi over 2. This would be 4 pi over 2, 5 pi over 2, 6, 7 pi over 2. So that's what that needs to be. So if we want to find out what theta needs to be, notice if we divide all of those by 2, theta can be pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. All of those values, aren't all of those between 0 and 2 pi? And all of those numbers, when we plug in for theta and double it, will give us something that makes cosine 0. So if we put in pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, those are where we're tangent at the pole. So if we sketch our graph, here theta is 0, and we're rotating around. When we get to here, theta is pi over 4. Then we're actually going to be coming down here. This is actually going to correspond to theta being pi over 2. Even though it's straight down, notice if you put pi over 2 in, what's 2 times pi over 2? Pi. What's cosine of pi? -1, because it's to the left. So this point is actually -1 pi over 2. Notice if we go in a direction pi over 2, -1 units, don't we go down 1? Yeah. So negative radius means we go away from that direction. So then as we rotate around, when we get to here, this is an angle of 3 pi over 2. Rotate around, this is at an angle of pi. I'm going to go past pi to 5 pi over 4. Then the angle we're actually plugging in and graphing is an angle between 5 pi over 4 and 3 pi over 2, but we have a negative radius, so we're on the opposite side. So this is actually a radius of -1 in a direction of 3 pi over 2. 3 pi over 2 is down here, but we're going away from it 1 unit to get to there. So that gives us that graph. So if we want to find this area, let's see, this was 0. When we got to here, this was pi over 2. When we got to here, this is 3 pi over 4, pi, and then this was 5 pi over 4. So we want to integrate from 3 pi over 4, add up all those sectors from 3 pi over 4 to 5 pi over 4. If we just want the area of just that one, then we wouldn't. If we want the area of the whole thing, yeah.
Since they're all the same, you could do like the right pedal and then just do the indoor 0 to pi over 4.
Yes. So if you do from 0 to pi over 4.
What is this? Flower art class?
How did you know?
It's pretty fancy.
It's Art Appreciation 102. Or what? Was it Art 1?
It's art radius equals cosine of 2 theta. Is that what that's?
Yeah. So that's how you generate that curve.
Really?
Mm-hmm. Lots of neat shapes.
Very interesting. What's all that stuff on there? Theta equals pi over 4.
These are just different values, different numbers you can plug in for theta to get a radius of 0. Which a radius of 0 means that you're not away from the origin, you're at the origin. Yeah. So, well, I appreciate it. So if you do that, that gives you half of the area of that pedal. So if you go from 0 to pi over 4, yeah, because so this would be in a direction of 0. This is the direction of pi over 4, so that would take care of that. So then that would give you half of that area, so then you would double it to get one pedal. Yeah. So what they were asking for is a 3 pi over 4 to 5 pi over 4, and then the radius squared.
Question on that one picture. The negative 1, 3 pi over 2.
Mm-hmm.
Where's the negative part?
Okay, so if you substitute 3 pi over 2 in here, 2 times 3 pi over 2 gives you 3 pi. 3 pi, that's over here. So cosine over here is negative 1. So we have a radius of negative 1 when we put, for theta, 3 pi over 2. So this direction technically is 3 pi over 2, but if we graph a negative radius, we go away from this direction 1 unit. I think I might have an animation that generates that curve. Let's see.
Can you work some of the later part of that chapter?
Sure. I've actually got the one for sine 2 theta instead of cosine 2 theta, which it works very similarly.
I guess maybe it was just messing with my mind as far as like, look, if you're looking for a point of negative 1, it just was in a different place.
Right. All right, so this is a little confusing, but let's look at what these pieces are. So the blue dot, that's the point that corresponds to the radius you get when you plug this angle in. So if we generate a table, if we plug in lots and lots of different angles, all right, this is the angle I'm plugging in. So as I let it play, like right now we're plugging in the angle 40. So notice our point is in the direction of 40. When I plug that in, I get a radius of 0.985. Right. So then as we go around, let's see. Here we're basically at 90 degrees with a radius of 0. So once my angle gets past 90 degrees, if I plug in something like 114 for my angle, when I double that, I'm going to get 230. If we think about the unit circle, 230 is down here, sine is negative in this quadrant. Sine is negative in this quadrant. So anytime if we're graphing sine, if when we plug our angle in, if that gives us something in the second or third quadrant for our answer here, we're actually going to get a negative radius. So even though the angle we're plotting is over here, since we have a negative radius, we plot away from that direction. So even though we're plugging in an angle over here, 166, our radius is negative, so we plot away from it. Then we get to a point where our radius is positive again, so we're plotting in the same direction as our angle. So right now, our point was following our angle. Now, our point is going to be on the opposite side from our angle because our radius is going back negative. So as long as our radius is positive, we're going to be graphing in the direction of the angle we put in as our input. But once our radius goes negative, we're going to be plotting away from the angle that we're putting in. So if I put in an angle like 40, I'm plotting in that direction because my radius is positive. But if I put in an angle like 120, I get a negative radius, so I actually plot away from 120. So this actually came from plugging in 3 pi over 2 in for our angle. We were plotting an angle that was from down here, but our radius was negative, so we plotted away from it. That's what makes it hard to find where graphs intersect sometimes, because if I intersected 2 graphs, let's say I took a circle and put on top of that. For this equation, that ordered pair is negative 1 3/2. For that circle, it could be that that point is just r equal 1, or that equation is r equal 1. So for one equation, that's a positive radius. The other one is a negative radius. So when you solve a system of equations, how are you going to find that? There's 2 different names. Remember when we solved systems of equations in rectangular coordinates, where they intersected, they have the same x and y value. But here, we just illustrated that we have the intersection of polar graphs, and they don't necessarily have the same r and theta. It could be that they have both the same. It could be that the r's are positives, but if they get there at different times in their cycle, then it could be that they're not the same points. So intersection of polar graphs in general is much harder. Now, a lot of them are straightforward if the points are the exact same coordinates, but if they're different coordinates, it is more complicated. All right, so you said, Conrad, some later problems in this section. So like 8. Okay. So they give us, this goes along with what we were just talking about. So they give us the graphs. And we want to find out their points of intersection. Now, we could probably look at the graphs and determine their point of intersection from the graphs, but the question is, how can we do this if we're not given the graphs? I suspect that that's the point of intersection. That looks like that's to the right, that our radius is 5, maybe in a direction of 0. Could be in a direction of pi. This is 5 units out. Remember, when we're measuring a radii, to the left is not necessarily negative. The radius is the distance from the center. So it could be that that radius is 5 in a direction of pi, or it could be that that radius is -5 in a direction of 0. We don't have any way of really knowing that until we solve the equations. So let's call this, let's see, I suspect this is R1 and this is R2. Yeah, because if we put a pi over 2 in, we get sine of pi over 2 is 1, so we get 2 times 5 is 10. So in a direction of pi over 2, we get 10. So that graph is R1. This graph, that is R2, which is this part. So if we want to find out where they intersect, we want to find out, well, where do they have the same radii? So we want to set these equal. Find out when is R1 equal to R2. If we divide both sides by 5, we can get rid of that. So that gives us 1 plus sine theta equals 1 minus sine theta. Let's move the sine thetas to this side, the 1s to the other side. So that gives us 2 sine theta equals 0. If we divide by 2, we get sine theta to be 0. So between 0 and 2 pi, notice they say only worry about positive radii. So if all the radii are positive, then these two will, it'll be when those two are both the same. So we're not going to worry about when do they have opposite radii with opposite angles. So if we consider our unit circle, at what two angles, or at what angles is sine 0? Zero and pi. That points in a direction of 0, and that points in a direction of 5. If we want to know the corresponding radii, we can look at the graph, or note if we substitute a 0 in, sine of 0 is 0, 5 times 1 is 5. Same thing, if we put a 0 in, sine of 0 is 0, 5 times 1 is 5. So they intersect at that point. If we put a pi in, the sine of pi is 0, so 5 times 1 is 5. Sine of pi is 0, so 5 times 1 is 5. So both graphs contain that point. Now, we got two answers for where we set those equations equal, but how many points of intersection are there on the graph? 3. So both of these graphs go through the origin, but they don't necessarily go through it at the same time or the same angle. Now let me see how they describe the answer to that part. So they go ahead and just say 0, 0 is a point of intersection. 0 degrees out in a direction of 0. It's not necessarily, notice the radius 0 doesn't actually occur at an angle of 0, does it? We saw a while ago when we put an angle of 0 in, we actually got a radius of 5. They just went ahead and gave us a name for the pole, but remember the pole, that can occur at any angle as long as the radius is 0. So, for example, this first equation goes through the pole. Let's see at what angle. If we try to find out when the radius is 0 there, divide by 5. That's whenever sine theta is -1. So that's at 3 pi over 2. So our radius is 0 for the first curve when theta is 3 pi over 2. For the second curve, if we set the second curve equal to 0, letting the radius be 0, that's whenever sine is 1, which is when theta is pi over 2. So r is 0 at pi over 2 on the second curve. But if the radius is 0, doesn't that describe that same point? So hence, as I was mentioning earlier, looking at the other problem, we have two different names for the same point. So when we solve our system of equations by setting them equal to each other, that point didn't show up. But that's somewhere we always need to check to see if both points go through the pole. If both points go through the pole, they may go through it for different angles, but they still have that point of intersection. All right. So we have those 3 points of intersection. So that was 8. Let's look at this one. Let's look at number 9. They ask us to find the area of the common interior. This will be about as hard as it gets out of this. In fact, it's hard enough on the standard. So this equation, that's going to give us a rose with twice that many, so 4 petals. You might have caught on by now, this is how that number is the length of the petal. Because if the maximum sine can be is 1, then when sine is a maximum, you get your maximum radius. If we have 4 petals, 360 divided by 4, we're 90 degrees apart. So we need to know where is the tip of our first petal. So sine is the maximum sine can be is 1, and the first angle that sine is 1 at is what angle? Pi over 2. So our first tip is at 45 degrees or pi over 4. If we put a pi over 4 in, notice 2 times pi over 4 is pi over 2. Sine at pi over 2 is 1, so we get a radius of 12. So let's plot that. 2, 4, 6, 8, 10. Let's call this 3, 6, 9, 12. So our first tip is in the direction of 45. And it's out 12 units. If we rotate 90 degrees, we're at our next tip. 90 degrees, we're at our next tip. 90 degrees, we're at our next tip. Also, if we look at our tangencies at the poles, let's think about when is this equal to 0. So that's equal to 0 when sine 2 theta is 0. And when we list our angles, since theta can be between 0 and 2 pi, 2 theta can go up to 4 pi. So sine is 0 at 0, sine is 0 at pi, sine is 0 at 2 pi, and at 3 pi. So if we divide those by 2, the angles for which our radius is 0 are 0, pi over 2, pi, and 3 pi over 2. So that's basically where we're tangent at the pole. That's where we're tangent at the pole. So if we sketch those at 0, pi over 2, pi, 3 pi over 2. So if we start sketching at 0 degrees or 0 radians, our radius is 0. Then our radius gets bigger and bigger and bigger till we get to 12. Then we come back to a radius of 0 when we get to 90 degrees. Then we're tangent. Come back until we're tangent. So there's our graph. So that's the graph of that first one. R equals 12 sine 2 theta. The other graph is what? R equals 6. What shape is R equals 6? It's a circle. A circle with a radius of 6. So, we don't want that to be filled. So what we're wanting to calculate is the interior area. The common interior, which is that 4 times. Now, that's actually a little tricky. Let me fix my red line here. Because if we want to calculate that area, remember our radius is what's varying. For the first little while, if I start in a direction of 0, and I'm wanting to go to the outside edge of this shaded region, let's call this R1 and the blue curve R2. So for the first portion, if I follow the boundary of the shaded region, is my radius defined by R1 or R2? R1. Once I get to here, if I follow my shaded region around, which curve is defining my radius, R2. And then when I get to here, I'm R1 again. So when we set up our integral, we can't just integrate one curve from the one side to the other, because for a time, our radius is given by R1. Then after we get to this direction, then our radius is determined by R2. And then when we get to here and go from here to here, our radius is back to R1. So let's see, let me sketch in. Let's call this theta 1, theta 2, theta 3, and theta 4. So when we go from theta 1 to theta 2, our radius is going to be R1. Also, when we go from theta 3 to theta 4, our radius is going to be R1. Aren't those the same? Isn't that symmetric? So if I break this up into separate areas, let's call this part area 1, this area 2, and that area 3. Notice area. So our total area of one of these, if we can integrate this part and get that area, we need two of those. Instead of having to do this integral, integrate it again from here, just find that area and double it, and then add area 2. Makes sense? So that'll give us the area of one of those. So for area 1, area 1 is half the integral from what? Let's see. We need to know what this angle is. We don't have that information yet, do we? So we need their point of intersection. So we need to find out, well, when do our two curves intersect? So when does 12 sine 2 theta equal 6? Isn't that R1 and R2? When is R1 equal to R2? Divide both sides by 12. So basically, when is sine 1/2? Now we could include all of the possible values, but we just need the first two. So if we want, well, what angles is sine 1/2? If we want the first two, notice sine is positive in the first and second quadrant. Sine is 1/2 at pi over 6. Sine is 1/2 also at pi over 6. So if we divide by 2, that's pi over 12. And what, 5 pi over 12? So that's where those two curves intersect. So if we look at our graph, this would be 5 pi over 12. What were they? Pi over 12 and 5. So actually that one's pi over 12. The other one's 5 pi over 12. This one is 5 pi over 12. Just make that make a little bit more sense. Pi over 12. If we convert that into degrees, take that times 180 divided by pi. That's 15 degrees. If we do 5 pi over 12, 5 times pi over 12, convert that, that's going to be 75 degrees. If this is 15 degrees, this is 5 times as much, 15 times 5, 75. So yeah, so our drawing's not off by far. So area 1 is going to go from 0 to pi over 12. And in that instance, our radius is defined by 12 sine 2 theta. We have to square that radius, and then that's d theta.
How did you know the intersection?
Because, here, because if I take the two radiuses and set them equal, if I divide both sides by 12, then sine is 6 over 12 or 1/2. Yeah, because we're looking for their intersection. Because where they intersect, where the blue curve and the red curve intersect, that's where we transition from our radius being given by R1 to our radius being given by R2. So that will give us that area. Then area 2, 1/2 of the integral from here, that's pi over 12, to here, that was 5 pi over 12. The radius, what's the radius in that section? 6. So r squared d theta. Well, that integral is simple enough. R squared, that's 36. Integrate a constant, you pick up a theta. So for time's sake, I'm not going to go through and integrate that by hand. We'll let MathCAD take care of that. Same thing here. Those are integrals that we've done time after time after time. So let's call area 1. That's half of the integral from 0 to pi over 12. And that was, r was what, 12 times sine 2 theta. I'm just going to use t for theta. That gets squared. D. So that's the exact value of that. How does it not want to give me a decimal approximation? I just do this. Well, we can get that. A2 is 1/2 of the integral pi over 12 to 5 pi over 12. That area, or that radius was 6 squared. So that's it as a decimal. I don't know why it's not wanting to convert it. Usually it'll convert it. If you do control period, it'll give you the exact value, and then if you match equal, it'll convert that to a decimal. So our area, we said for one of those, we need an A1 twice, so we need 2 A1s plus A2. So if we do 2 A1s plus A2s, that gives us the exact area of one of those, and then how many of those things do we have? We had 4 of those, so that gave us this total area. We do 2 A1s and an A2, that gives us all of that, and we have that 4 different atoms. So if we take that area times 4, that's the exact value. If we just need that as a decimal, about 88.4, which let's see if they got it right. They gave the exact value. (48 pi minus 36 square roots of 3). So the integral, while we didn't do the integral wasn't too bad. This integral was very easy. This integral, we would have had 144, which we could have pulled out front. Sine squared 2 theta, and what do we do when we have to integrate sine squared? Use the double angle identity. So the biggest thing was graphing it. Going ahead and putting in our polar tangencies for our rows. That way we could tell where this section of the rows started, where this section of the rows stopped. That section of the rows went from 0 to 90. We drew in our other curve, and notice also I drew a ray through our point of intersection, so we could see, okay, for this area, our radius is given by this curve, R1. For this section, our radius is given by R2. So then we could integrate appropriately. From this angle to this angle, our R1. From this angle to this angle, our R2. So in general, getting the graph and getting our angles there is probably the messiest part. And technically all that part is really true. We didn't do most of that, or we didn't put all of that together in trig. I guess half of y'all, well, Conrad, you didn't have me for trig either, did you? So I guess only one of y'all had me for trig. So I guess you're the only one, Craig, that we did that stuff in trig, but we didn't ever put all of that together. So if you took trig here, or if you placed in the 125 and took trig in high school, all of the graphs are things you've done before, you just haven't done it all together. You probably haven't actually found points of intersection, but that's just solving the system of equations. All right. Let's do, at least set this one up. Number 10, yeah. So let's look back. If we want to graph this, r equal 2 cosine theta, we actually have that somewheres. I think it's at the bottom of this previous page. Here. If we have r equals a constant times cosine theta, not 2 theta, 3 theta, 4 theta, 5 theta, that's a circle to the right of the origin, goes through the origin, and the constant out front, that tells us the diameter of it. So if we have r equals 2 cosine 2 theta, that's a circle with a diameter of 2 that is on the right side of the origin and touches the origin. So if we, if this is 1, 2, then that's a circle right there. Notice if we take r equals 2 cosine theta, when theta is 0, cosine of 0 is 1, 2 times 1 is 2. So this point, it has a radius of 2 when our angle is 0. In the direction of 90 degrees, if you put a 90 degrees in, or pi over 2, cosine of 90 is 0. So this point has a radius of 0 at a direction of pi over 2. So this part of the curve, that goes from 0 to pi over 2. When we go from angles from pi over 2 on to 180, if you think about the unit circle, from pi over 2 to 180, is cosine positive or negative over here? Negative. So if we pick an angle over here, our radius is negative, so that's going to start giving us this part. Even though our angle that we're putting in is an angle over here, when I put this angle in, I get a radius away from it. When I put this angle in, I get a radius away from it. When I put this angle in, I get a radius away from it. So that's going to generate that bottom part of that circle. You don't have to know all of that. You just basically need to know this. But that's where that curve comes from. So that's that. And then the other one was r equals 1. So that's r equals 1. That means no matter what angle we pick, we always have a radius of 1. So that's a circle centered at the origin with a radius of 1. So they ask us for the area inside the circle on the right, outside of the circle centered at the origin. So inside here, inside this circle, but outside this circle. So it has to be outside that circle, but inside that one. So it can't be that part because it's not outside this circle. So it's what, just that part? So that's the area we want. So if we call this R1 and R2, then let's see. I'm going to adjust our coordinate system just a little bit so this is larger. Let's undo that. Let's delete this. Let's call this 1 unit and this 2 units. So if we have a diameter of 2, not that, then our R1 is here. Our R2 is correct. Our R2 is a radius of 1, so there. So that just makes it a little bit larger, a little easier to see. So if we're wanting this area, we could get that area a couple ways. So if we go from here to here, if we integrate this outside circle from here to here, so let's call that theta 1 to theta 2. So if we integrate, let's see, is this is R1, this is R2. So if we integrate R1 from theta 1 to theta 2, then we're going to be following that along. And notice that's going to give us all of this area. Isn't it? Isn't that right? So if I start with theta 1 and I follow the first curve around, it's going to give us the area from this to here following that curve. So let's call that area 1. So that total area, not counting that, is area 1. So if we could get rid of that part, wouldn't that give us that area? And isn't this total area just twice that? So if I can get this area, then my total area is just twice that. So I can get this area in here. Notice this radius is the second curve. So I just need to integrate. If I call this area area 2, that's just 1/2. This is my radius. If I let my radius be this one, that's just this sector. So R2 squared d theta from theta 1 to theta 2. That makes sense. So we go from here to here. That's going to be this area in here. So that's going to be from theta 1 to theta 2, letting our radius be given by R2. So we'll call that area 2. So if we take the area 1 is 1/2 the integral from 0 to, we need to know that angle. So that angle, that's where our two curves intersect. So that's where 2 cosine theta equals 1. That's where R1 equals R2. So if we divide by 2, what angle is cosine 1/2? That's cosine is 1/2 at 60 degrees or pi over 3. So for 1, we go from 0 to pi over 3, integrating 2 cosine theta, that's our R, squared d theta. Our A2, let's move this over, not all of that over. Our A2 is 1/2. Integrate from 0 to here, pi over 3. This radius, which that radius is a constant, and what's that radius? 1 squared d theta. So if we get both of those areas, we take that whole area, A1, subtract off A2. So that gives us that part. So if we want our total area, we just double that. This integral, that's simple enough. We're integrating a constant, so we pick up our variable. Here, we're integrating 4 cosine squared, so we have to use our double angle identity. So doing a lot of integrating cosine squared, integrating sine squared. All right. I think that's got it.
And you're going to give us
The graphs?
yeah, the shape.
Yeah, I'll give you the formula sheet. It's got the different shapes on it. Then you'll just have to, depending on what equation.
One you kept looking at. Or like that.
Yeah, it'll look like that. So I'll basically print that off and give it to you. So you whatever function I give you, polar equation I give to you, you'll just use that to translate that into your graph. And I'll give you a polar coordinate system so you can use that to sketch your graph on. So make your formula sheet. No sample problems on it. Was that the only thing that I said I was going to give you? I'll give you this, and then y'all would write the formulas down. Yeah. It was the last test I gave y'all that chart from the series. Yep. All right. Any other questions?
What about our last two tests? Great.
Tomorrow, when I'm giving finals, before I start grading finals, I'm gonna grade my old test. So y'all's is at the top of the list, close to the top of the list. I'm finishing up a Math 100 test right now. That's probably the longest and the most number of students I have left on the test to grade. Once I get it graded, then I just have y'all's two tests, a linear algebra test, so there's just 4 people in, and then a Math 098 test. I'll probably do the 098 last because I think theirs was the last. They were the last ones to take the test. So I'll probably try to get the Math 100 test. I'll do y'all's test. And it shouldn't take me long to get those knocked out. So, when's y'all's final? Tomorrow at 1? I'll probably have at least one of y'all's test graded by then.
Oh, that's 3.
Yeah. Then, yeah, I should have it done. And then, while y'all are taking y'all's tests, I'll probably be working on the other one. So by the time y'all leave, I may know both of y'all's test grades. But from what I understand, the final is going to replace one of those 2 tests for most of y'all. Maybe not. Maybe y'all all made hundreds on those 2. But, from what I understand, that last test was a little bit of a booger.
Yeah. There was like the problem first page I didn't quite read it right. Like I couldn't tell if it was a negative. The next one was negative.
Oh yeah, because it looked like it had an equal in front of it. It was supposed to be a
But
negative.
I thought maybe it was a negative.
It was a negative.
Okay, well,
Yeah. Yeah.
And that very last one, I'm not sure if it was 11. It was like the Taylor series.
Right.
The Taylor polynomial.
Because the Taylor polynomial is when you do a finite number of terms. So you just list the terms. The series is when you write it in terms of a summation.
Yeah.
So you list like the first 5 or 8 or so many terms, and then you come up with a formula for
I
it.
tried to do that. I couldn't get them to come up. I mean, I think I found one that would come up with like the first 3 or 4 of the series.
Gotcha.
The first 3 or 4. I think I got all the ones I did.
Okay. It could be that one of the later terms you might have had wrong or something. So it could be, if you got something that came out for the first 3 or 4, it could be right. Excuse me. Anything else? Let me stop making this video real fast.